Thanks everyone. Good morning and welcome to today's webinar. My name is Alison Starkey and I'm the Communications and Marketing Officer at SRA. Today, Sijesh Natarajan, a Principal Researcher at SRA in the Burdekin, will be presenting on the topic of drones use in SRA plant breeding, high throughput phenotyping to improve clonal selections. The webinar will consist of a presentation for around 45 minutes, followed by a Q&A session for about 15 minutes. And during the presentation, I'm sure you're all kind of familiar with this now, but we'll just check that your microphones are all on mute. You can type questions into the chat function at any time, and Sijesh may answer those as he's going, or we may hold those until the end. If you're not familiar with that, the chat function is the little speech bubble icon that is sort of the second one from the left on the top bar across the top of your screen. During the Q&A session, again, you could either type a question into the chat function or you could raise your hands to let us know that you would like to ask a question. And to do that, you click on the third icon from the left, which is the little picture of the face and the hand raised, and then we'll be able to kind of address the questions or call on people, make it a little bit easier for everyone to ask their question and to hear. And then please remute your microphones after you've asked your question. At the end of today's webinar, it would be really helpful if you were able to complete a very, very short survey, and I'll put the link to that in the chat. So it's just a Microsoft form. I think it'd be less than 2 minutes. It really helps us. And also at the end of today, or sorry, later on today, the recording of the webinar will be uploaded. So I've already had a couple of questions about access to that. So yeah, that's generally pretty quick for us to turn that around and have that available. If you would like to review it or to send the link to anyone else, you can do that as well. So I'll just give you a bit of an introduction to Sijesh, and then he'll take over. So he's a phenomics scientist based at SRA. He received a Master of Biotechnology with specialisation in molecular plant breeding from RMIT University. He is in the final stages of the PhD in sugarcane crop physiology at the University of Queensland. In his current role, Sijesh employs high throughput phenotyping, remote sensing and crop modelling approaches to identify novel traits and to develop clonal assessment techniques for making informed variety selections in the SRA plant breeding program. So I'll hand over to Sijesh to take us through his presentation.
Thank you very much, Alison. Welcome everyone, and good morning to all. I'm going to talk about the use of drones and sensors for high throughput phenotyping. So firstly, I'll give you an introduction to high throughput phenotyping, and then I'll go on to talk about how we are using those techniques for improving clonal selections in the SRA breeding program. So what is a phenotype? So phenotype is the morphological, physiological, and performance characteristics of a plant. And it is the result of combination of the genetic makeup of the plant and how it interacts with its growing environment, which could be the soil, the farm management, or its interaction with biotic and abiotic stresses. So those interactions lead to the phenotype. And it's important to remember that a genotype can have a different phenotype depending on its growing environment and how it interacts with that environment. So the ability to phenotype accurately in those different environments is critical to evaluate the true potential of a genotype and also to make good breeding progress. Now, phenotyping is not new. Measuring yield, for example, can be termed phenotyping, but in this case, phenomics or high throughput phenomics refers to the use of remote sensors or drones and the advanced image processing methods for capturing some of the traits with high accuracy, high affordability, and high throughput. So in a few years' time, our ability to phenotype some of the morphological and physiological traits has improved dramatically. If you look at this graph of the cost and affordability of phenotyping some of the traits, So measuring some of the physiological and agronomic traits using manual methods or using traditional methods is extremely time consuming and extremely expensive. But with drones and remote sensors, we are able to phenotype the same agronomic and physiological characteristics with quite low cost and with quite high throughput. So the ability to phenotype some of these traits has improved dramatically in the last few years. So these traits have gone from unattainable in a breeding program to being low cost and easily attainable, such that we are even easier to attain than a plot yield or NAR-based sugar content. Now, they're not only cost effective, but also there are several other benefits. So firstly, they are non-invasive or non-destructive. That means you can have a temporal assessment of a plant and monitor its progression or growth over a period of time, or over a period of time, you can see how the plant responds to stresses or abiotic stresses. And also with high throughput phenotyping, we can capture multiple traits at once. And we can also capture some of the traits that would really be unfeasible using traditional approaches. For example, simple things as plant height. They will be really hard to measure in the breeding program, especially later in the crop stage. But with the drone, you can measure that in a matter of minutes at all stages of the crop. And not only that, all the traits that we measure using a drone or of high accuracy, we can get really centimeter level precision accuracy images, and we can use that to extract traits with really high accuracy. And not only that, it also takes out the operator and also the human error out of the equation. Now, phenotyping is a little bit different to precision agriculture. So they share the same principles and the similar methodologies. However, the primary objectives and the challenges associated with each of these are quite different. So in precision agriculture, you're dealing with capturing the spatial and temporal variation in the crop and soil. And what you're after is actually some real-time information or close to real-time information so that you can make a quick farm management decision. Whereas with phenotyping, we want to assess which genotypes perform well under certain environments. But the challenge with the phenotyping is that we are dealing with the big data. So we have thousands of plots and which have been measured over a period of time. And the challenge with phenotyping is to how to make sense of that big data. So these two precision agriculture phenotype, they share similar methodologies, but the objectives and the challenges are quite different. Now, phenotyping can be broadly classified as under controlled environments or under field environments. So controlled environments is that you have complete control of the environment. So you can control all the environmental variables in a chamber such as these and have one variable that's changing, and you could have the plant characterized for that particular environmental variable in a detailed way. So you can have a detailed characterization under controlled conditions, but one of the disadvantage of that is that you will need to validate some of the results from controlled environment phenotyping under field conditions to make sure they perform well under natural conditions. On the other hand is the field-based phenotyping, which is out of control. That is, you don't have any control over the environment, but you could have a higher throughput with field-based phenotyping. And also all the phenotypes are captured under the natural environment. So that's a big advantage with field-based phenotyping, but in practice, you will need both. To characterize the plant under controlled conditions and to develop some models or algorithms or spectral profiles, especially for complex traits, and then bring over those models onto the field and test them in the real environment. So they go hand in hand. You need both to make good progress with phenotyping. Now, the field-based phenotyping can be done at different scales. using ground vehicles, using the drones, using manned aircraft, or using satellites. Again, each have their own advantages and disadvantages. Early on in the breeding, in this project, we tried to use some of these ground vehicles, but as you can imagine, in sugarcane, it's quite difficult to use at 3 or 4 month stage once the sugarcane reaches a meter or two. But it's quite extensively used in other industries, in other crops such as cereals and rice. So it's quite useful for phenotyping other crops, but not just for sugarcane. Manned aircraft are quite expensive, and for everyday breeding activities, it's quite unfeasible. The satellites are getting better and better with each commercial launch, but yet the most highest resolution you can get for multispectral imagery using satellites is about 1.2 meters, which is still quite low to phenotype breeding plots, to phenotype small plots. So the technology is still not there yet from the satellites to do field-based phenotyping. On the other hand, the drones, they are almost tailor-made for phenotyping in the field conditions. So the drones are getting cheaper and cheaper, but the technology on the drones is getting better all the time, and they can carry multiple cameras. They are easy to operate, and they're quite inexpensive to operate as well. So they're almost tailor-made for field-based phenotyping. They can fly at low altitudes and can get really high-resolution imagery. Now the drones can be equipped with different kinds of sensors, visible, multispectral, thermal, or hyperspectral, and there are others such as LiDAR and fluorescence spectroscopy. But what each of these sensors does is they capture certain regions in the electromagnetic spectrum, and each of those regions contain specific information about the plant that we can understand. For example, from the visible region, we can understand more about the the structural characteristics, or such as plant height, the flowering, etc. And by measuring reflectance in the multispectral region, or in the shortwave, infrared, and the NIR region, we can generate vegetation indices such as NDVI or NDRE or chlorophyll indices, which is an indicator of the plant health and also the photosynthetic capacities of the plant. And by measuring imagery in the long wave infrared region, we can generate thermal images such as these. And from the thermal images, we can measure canopy temperatures. Canopy temperature is a function of the water use of the plant. So the more the plant uses water, the more cooler the canopy. And that's quite useful because it integrates both the water use and the photosynthetic capacities of the crop. And with hyperspectral sensors, we can measure wavelength in the entire visible as well as the shortwave infrared regions. We can measure several wavelengths from 400 to 2500 nanometer. And as you can imagine, that contains a lot of information, including information about the chlorophyll pigments, carbohydrate concentrations in the leaf, and also we can generate some spectral profiles of diseases or some pathogens. Now, in terms of the phenotyping platform that we have here at SRA, so it's mostly based on multirotor such as these. Now, the drones can be either multirotor or a fixed wing, and again, they have their own pros and cons. A fixed wing can have a much more stable flight and they can fly for longer, whereas multirotor such as these are easier to operate and they can have a vertical takeoff and landing. But one of the disadvantages of a fixed wing is that you will need a dedicated landing and takeoff pads, and they are quite difficult to operate. There are a lot of power lines and things like that around. So for our purposes, these multirotors work pretty well. They are easy to operate, and they can carry multiple cameras, and they can have a flight time of about 20 minutes, enough to capture images at high resolution in a 7-hectare block. And as I said, the drones can be equipped with different kinds of sensors, RGB, multispectral, hyperspectral, or a thermal camera. And each of those cameras provide specific information about the crop. Now, all of our workflow is semi-automated, which means just a few click of the buttons, we can have the outputs generated quite easily, and all of the data is in a cloud-based application, so that the breeders can use at any time. So to give you an idea of the processing pipeline that's being used here, it's quite general across all phenotyping applications. So the first step is a mission plan, which is to generate a grid flight path on the field of interest. So the objective here is to optimize the flight time and flight speed and the image overlap to make sure we can complete the flight within the drone battery limit of 20 minutes, and also to have a high resolution imagery. So we usually aim for a ground sampling distance of 5 centimeters, which means that each pixel in an image represents about 5 centimeters on the ground. Now the drone flies autonomously along this path, and as it flies, it captures a series of high resolution images. And these images are then fed into a software, which then stitches it up to give us a image such as this, which is called an automosaic. And once we have the automosaic, we can use some GIS techniques to extract plot level data from these images. And depending on the type of camera that we used, we can extract different types of data from these images. And all of this data, as I said, is fed into an online application called Trait Explorer. And that application allows the breeders to generate reports or plots and do some statistical analysis on the go. So in a matter of hours, we can have the drone capture the pictures and the images processed and have actionable data in about a few hours' time. Now, the basic goal of phenomic research at SRA is to overcome some of the bottlenecks of the conventional phenotyping and to have a phenotyping approach that is more comprehensive, more accurate, and higher throughput. So how are we going to actually achieve this? Is easier to understand by looking at this equation, which is called the breeder's equation, or the equation for genetic gain. So the genetic gain can be increased by either increasing the selection intensity, or by improving the selection accuracy, by increasing the genetic variance, or by reducing the years per cycle. Now, because the drones are high throughput and they're cost effective, they can help in phenotyping a larger population and thereby increasing the selection intensity. The selection accuracy can be improved by improving the heritability of the traits through more precise phenotyping, and by improving the quality of breeding trials by reducing the error variance in breeding trials. So the drones can help with that. And also, as we know, there's a narrow genetic base in sugarcane, which is one of the bottlenecks for genetic improvement. And that issue can also be effectively addressed by phenotyping several novel traits or functional traits, such as canopy temperature, which is quite difficult to measure using traditional methods, but with the drone and the remote sensor and a thermal camera, it's pretty easy to measure canopy temperature. And also there's, because the drone measurements are in general non-destructive, there are opportunities to reduce the years per cycle through some predictive breeding and non-invasive phenotyping approaches. So I'll dwell more into how we are targeting each of these components a little bit later, but in this slide, I'd just like to refresh the different breeding stages at SRA. So the first stage is called the progeny assessment trials, or PATS, where about 100,000 seedlings from a few different crosses are tested. and they are planted in single rows. And the selection is based on family means of TCH, CCS, and fiber, and also end of season assessment, visual assessment by the breeders. And from stage 1, about 12,000 clones are being progressed to stage 2, which is called the clonal assessment trial, or CAT. And in the clonal assessment trial, they are again planted in single row 8 to 10 meter plots, and they are selected for TCH, CCS, fiber, and some diseases. And in stage 3, which is called the FATS, or final assessment trials, about 1,100 clones are being phenotyped. And these not only include clones from stage 2, promising clones from stage 2, but also elite clones from previous years or from other regions. They are tested in partial rep trials across multiple locations in 10 meter by 4 row crops or plots, which we assume is under pure stand conditions. And they are again selected for TCH, CCS, fiber, and diseases. And it could take up to 12 years to from crossing to have a variety released. Now, the primary breeding objective is to improve the productivity on growers' farm, which is under pure stand conditions. So ideally, we would like to test all the clones under pure stand conditions in multiple environments, but that's not feasible in early stages of breeding because mainly because we are limited by the amount of seed material that is available. And usually the breeders like to have a bigger population so that you have a better chance of finding a good clone. So they usually have to have a balancing act of having a bigger population and optimizing the land resources. So in early stages, the clones are tested in small single row plots in single environments. But testing clones in such small plots in single environments can be quite problematic, mainly because it's quite difficult to phenotype accurately in such plots. And it's quite difficult to evaluate the true genetic potential of the clones in such small single row plots. For instance, in a cat trial, in this cat trial in 2016, we can see the TCH data was associated with a large error. The TCH varied from 0 to almost 280 or 300 tons per hectare. And these are only 6 meter plots, so some of these values are quite clearly not representative of the true phenotype of the crop. And on this graph, if you look at some of the standards from that trial, and if you can focus on the Q2O weight, you can see again the TCH varies quite a bit from 100 to 260 tons per hectare. So there's quite a bit of error in estimating plot yield from single row crops. They could be due to several reasons, but one of the foremost reasons could be in small single row plots, there is confounding interplot competition effects. So here on the graph on the left-hand side, we can see for the same set of clones that were tested in a 4 row and in a single row. And we can see that in single row plots, the genetic variance of TCH is quite inflated compared to the 4 row plots. And this generally indicates that the crop has significant competition effect for TCH. In comparison, we can have a look at CCS or fiber, and we can say that the genetic variance is not that inflated under single row plots for CCS or fiber. Another way to look at it is so the competition effect is when a plot is or when a genotype is being influenced by its neighboring genotypes. So you can imagine a shorter genotype would have significant competition for light due to shading from its neighboring plots. So in such cases, it's quite difficult to phenotype the shorter genotype quite accurately, or to measure its true yield potential in such competitive environments. And this graph shows just that. So on the x-axis is plot yield, and on the y-axis is the difference in the neighboring plots, average of the neighboring plots and the plot values. So what this graph shows is that the taller the neighboring plots, the lesser the yield of the actual plot. And similarly, the more vigorous the neighboring plots, you get lesser the yield. So these evidences clearly show that in the CAT trial there are significant interplot competition effects, and they can really affect the clonal ranking for TCH, and also bias the selections in favor of more competitive clones. Now, another issue is lodging, which is just not prevalent in all the regions, but quite predominantly in Bergen. So here we are looking at a part of the CAT trial, CAT block, and how it progresses from October through to March. And if we can focus on NDVI and its heritability. So heritability is the proportion of variation which is due to genetic effects. So you could think of it as accuracy of the phenotype, and the closer they are to 1, the more accurate they are. So in October, we could see that NDVI values were around 0.67, and as we move through to December, 0.7, February 0.8, and when we get closer to March, there could have been a lodging event or just competition effects, and we get a really poor phenotyping accuracy. So it shows that as we move towards the harvest season, as the crop grows larger and larger, our ability to phenotype small single row plots is diminished. Yeah. So that's one of the issues that could be affecting the plot yield estimations. As you can imagine harvesting this crop using a huge harvester and getting an accurate phenotype could be quite problematic. The other issue is that the CAT trials are in general really large, and about 6 to 7 hectares, and they can be associated with significant spatial variations. Now, all these spatial variations are not accounted for using statistical methods, or they're quite difficult to account for when there is a huge spatial variation using statistical methods, and that can also contribute to the error in plot yield. So all these things, what it means is that it results in the low heritability of cane yield in single row plots, especially in CAT. So on this graph, we can look at the heritability of CAT from 2015 to 2016 series in a region. And we can see that heritability ranges from around 0.4 to 0.6. I mean, compared to a fat trial, it's quite low. And what also it means is that there is a poor correlation between single row cane yield assessment and pure stand cane yield assessment. So on this graph on the right, we can see the CAT series clones, the correlation between CAT series clones and the fat plant crop. Usually there is multiple fat crop, multiple plant flat crop. In this case, in 2009 there were 3, in 2010 there were 4 fats, and so on. So we can see the phenotypic correlations. They are in the range of 0.2 to 0.5. So they're quite low, which means that the clones that perform well under CAT conditions, they don't show the same level of performance under pure stand conditions, and that really can hinder the breeding progress and the genetic improvement that we can make effectively. Now, one way to address this issue, mainly the interplot competition effect and effects, and to improve the selection accuracy in the CAT trial, is through the use of indirect selection indices. So indirect traits are those traits that are captured from a drone. They are yield determining traits. They are called indirect traits because they are not of direct economic importance, but capturing those may help to improve the traits of economic importance, in this case cane yield. So we looked at 3 indirect traits: the canopy height, the canopy cover, and NDVI of the plots. And the indirect traits could be quite advantageous because, firstly, the indirect traits have high heritability in single row crops. For instance, in this trial, the heritability ranges from 0.68 to 0.79, and this is in comparison to cane yield 0.5. It's quite good. And they have a better correlation between single row and pure stand conditions, so they seem to be less affected by interplot competition effects. So we can see for canopy cover, the correlation coefficient is 0.77, and that's in comparison to for plot yield, which was around 0.5. And they also provide good correlation with pure stand conditions. So under pure stand conditions, these indirect traits are quite well correlated with pure stand cane yield. So all these things put together, they make them good candidates for indirect selection for pure stand cane yield and single row plots. And the other advantage of the indirect selection is that we can move the selection before the onset of competition effects. Effectively, we can move the selection to this stage where we can phenotype the plots really much more accurately than at this stage. So the question is, does indirect trait-based selection in single row plots provide a better selection than single row cane yield? And does that improve the genetic correlation between cat and fat? So that's what we tested, and we developed these two different selection indices, one based on plot yield selection, other based on the indirect traits-based selection, and we looked at the correlations of the ranking of the clones using these two approaches. And you can see that there was quite a significant difference between the ranking of the clones. And if we looked at the top 250 clones that would normally be selected, there were about 112 clones common between these two techniques of selection. So about 45% of the clones were common. Now the question is, which of these two selection methods is better? So a correlated response to selection for pure stand cane yield was 0.73 for NDVI. That means they are 73% as effective as direct selection for pure stand cane yield, whereas for single row cane yield it was 45%, so they are only 45% as effective as direct selection for pure stand cane yield. So theoretically, to answer this question, theoretically, yes, the indirect selection provides a better approach, but we are in the process of validating these experimentally and also developing selection indices or separate selection indices for rain-fed and irrigated conditions, and also incorporating some other additional indirect traits such as canopy temperature into the equation. Another component that significantly impedes the precision of phenotyping or the heritability of target traits is the huge spatial variation that we often see in breeding trials, especially sugarcane breeding trials, and some discrepancies in the plots, such as plot gaps. So those things are generally not accounted well in the breeding program because generally they are very difficult to measure using traditional approaches. So measuring the plot gaps, 3,000 plots is quite difficult. But with phenomics approaches, we could effectively capture a number of spatial and plot-based covariates and use them as covariates in a breeding trial analysis to improve the precision of the phenotype. So in this slide, this slide shows that the aerial phenotypes such as NDVI and canopy height can effectively capture soil variation due to soil EC. Now, most trials would have soil EC data by themselves, but this can provide an additional layer of data for covariate analysis. And they have the advantage that they capture the actual crop growth at the specific location rather than just looking at the physical properties of the soil. The next thing is, as I said, there could be discrepancies in the plot, such as differences in plot length. It's usually assumed that all the plots are of same length, either 8 or 10 meters, but in reality, they could be of different lengths, and accounting for these different lengths in the plots as using plot length as a covariate in breeding trial analysis can also contribute to improving the heritability of some of the traits. In this graph, what we are looking at is actually the TCH of the plots and the TCH of the plots corrected for covariates using plot length. And you can see whether you use the non-covariate model or the model with the covariate, there could be differences in the selections that you would make. And we have seen some good improvements in heritability using plot length as covariates in some of the trials. So it generally depends on if the plot gaps are due to actual environmental errors or it's due to the genotype. So by statistical analysis and by using them as covariate and looking at the improvement in models, we can figure out if the plot lengths are useful in analyzing particular trials and in improving the traits for particular trials. And we could also capture other covariates such as germination or stand count and a lodging index. So we can capture all these traits and we can make these data available to the breeders to use them as covariates for statistical analysis, and it boils down to the breeders to find the covariates that they would think would improve their trial precisions, and we are in a position to capture these traits quite easily from the plots and provide them with the plot level data for further analysis. Now, another component of the genetic gain equation, if you like, is the selection intensity, and using drones, we could effectively improve that as well. So if you look at the pads, they have similar challenges to cat. They have high competition effects between and within families because they are planted in close proximity, and they are based on visual assessment by the breeders, which can be subjective. So some breeders might look of some plants, some breeders might not. But the third issue, and which is potentially a big issue, is that some progenies can be overlooked if we just go by the average of family means. For example, in this graph here, we can compare cross A and cross B with the standards. So this shows the NDVI of these crosses, and in most cases, the cross B would be ignored, and no progenies will be selected from cross B because they have below average performance than the standards. But if you actually look at the progenies from cross B, some of them were better performance than standards, and even better performance than maybe a proven cross. So there is potential for overlooking some of these progenies when we just go by family means. But with high throughput phenotyping, we can capture indirect traits or vigor traits from each of these the progenies from each of the seedlings, and that would help to make sure we don't overlook any of the promising progenies. And it also provides an opportunity for the breeders to identify those progenies early on in the crop stage and monitor the progression of those progenies over time. And And in general, they just provide another layer of data. So a breeder at the end of 12 months can have a look at the plant, and he can also look at his tablet and see how the crop looked at 3 or 6 month stage. And that would enable better decisions in selecting the progenies from a plant. Now, another component is targeting some of the novel traits and incorporating them in breeding programs. Years of research have shown that canopy temperature is potentially quite important for improving yield under rain-fed and irrigated conditions, because they integrate both the water use and the physiological characteristics of the plant. But they are quite difficult to measure. But with phenomics, it's becoming a reality to measure them with good accuracy. Now, researchers have also shown that high selection pressure for canopy temperature may not be very useful, because it can result in some clones that are slow growers, and they might lose out in environments with good water, good irrigation. So to overcome that, one approach would be to select for the combination of canopy temperature and also vigor and yield in a selection index. So for example, if you look at this graph, the genotype Q232, it has high yield characteristics, and it has low canopy temperature, which means that it uses a lot of water to produce its yield. Whereas genotypes such as the 2583, it has similar or slightly better yield than Q232, but it uses less water because it has higher canopy temperature. So we could say that this genotype may be particularly suited for water limited conditions. And one way to use this information is we can measure these novel traits in an integration program and to identify promising parental material. So that would also overcome the bottleneck of narrow genetic base in the sugarcane germplasm. Now this slide is to show that it is not all about field-based phenotyping. You would need some controlled environment phenotyping, especially for some of the physiological traits such as transpiration efficiency. Now, transpiration efficiency can be highly affected by VPD, which is the difference in vapor pressure between the leaf and the atmosphere. And in this study, we looked at a bunch of genotypes and how they responded to high and low VPD conditions. And the genotypes responded quite differently, but overall, there was no G by E for VPD and transpiration efficiency. So we can take this information or this knowledge into the field-based phenotyping and say and have the confidence that phenotyping of the clones under different VPD conditions would not necessarily result in different ranking of the clones. So both field-based and controlled environment phenotyping would be important for, especially for physiological traits such as transpiration efficiency. Another thing we looked at is yield predictions of ratoon crops. So the drone observations, they provide good prediction of cane yield even in unrelated years. So over here on the left-hand side, we use indirect traits measured in the plant crop and the yield measured in the plant crop to predict the yield, and we could do that with good accuracy of about 0.82. What we could also do is we can take this model that was predicted in the plant crop, and we can use that to predict the yield of the ratoon crop, and we were able to do that with an accuracy of 0.65. So what this means is that we could save a bunch of money and also time by not harvesting the ratoon crops, successive ratoon crops, and by just predicting their yield based on the indirect traits. And because the crops are growing on the same plot across different years, we can have some good statistical methods to make the predictions, or machine learning techniques to make the predictions. So this is sort of a phenomics roadmap that we have assembled so far here at SRA. So you can see this is how the breeding program progresses from integration program to crossing through to release in up to 12 years. Again, this is just a representation, and there are variations of these at different regions. This would represent one of the central region breeding program. So as we can see here, the phenomics, they can have a positive role or have a positive role to play in each of the breeding stages. So for example, in the integration program, we can use the phenomics to identify novel traits such as returning ability or canopy temperature of the clones. And in the patch stage, we can use phenomics to identify progenies or have quantitative data for progenies instead of having family means. And in the cat stage, in general, we could use phenomics to improve the heritability of the traits or the target traits, and also to improve the selection accuracy using indirect selection approaches. And in the fat stage, again, we could have a higher heritability of cane yield using spatial covariates. And in the second return crop, we could have some yield prediction models so that we don't really have to physically harvest the crop. So this is a baseline scenario. That's what we can do now, or we are doing now. But going into the future, in the next 3 to 5 years, we also hope to do some things like phenotyping the crop for important leaf diseases and using them for clonal rating. We're already working with some of the SRA pathologists on this, and also modeling the pure stand cane yield so that we could, instead of 4 rows, we can possibly have 2 rows and improve the selection intensity in that way. And some other things such as predictive breeding. So can we use phenotyping, genotyping, and enverotyping to identify traits or combination of traits or alleles or combination of alleles to say they would be suited for specific growing conditions or for specific seasons. And also, we have seen that a preliminary study that there is potential for hyperspectral reflectance in predicting foliar sugar content, and can we use that to predict actual sugar cane content, and that's again on the horizon. So in summary, the ability to phenotype effectively is one of the bottlenecks that limits genetic improvement in sugarcane because of its long crop cycle and its high phenotyping error. Phenomics is actually maybe quite important for sugarcane breeding and for genetic improvement in sugarcane breeding. And we need all these innovative approaches to try and improve the rate of genetic gains in sugarcane, which has been quite stagnant for the past decade. And also, so far we have showed that the drone-based methods have high potential for improving selection and for effectiveness of the breeding program at different stages. But again, it's not the solution for all of the problems, but it can play phenomics can now play a positive role in augmenting some of the other innovations that's going on in the SRA breeding program to try and accelerate the rate of genetic gains. And with that, I'd like to thank Johan, who's our pilot, who captures all the flights and data. Shiming and Jason, who always come up with great ideas and who do the big picture thinking. And big thanks to the entire plant breeding team at SRA, the Brandon team, Ingham team, and George and team and Mekai. And also thanks to the communications team for this webinar and for all the previous communications. The funding unit, Harjit and Stephen, and Lauren, who's our engineering consultant, and Jaya, Prakash, Phil, and Scott, who were ex-team members and who were instrumental in getting this technology to this stage in sugarcane. Yep. With that, I'd like to thank you all for listening, and happy to take any questions.
Thanks very much, Sijesh. There's actually already one question in the chat. So the question was from David, and are the drones and sensors owned or rented by SRA?
David, they are all owned by SRA. We have remote pilots, qualified remote pilots who can operate the drones. but because our drones are pretty big, we need to have a operator certificate, so to say, and we depend on, as I said, a law in Toowoomba to have that operator certificate. So yeah, we rely on some external people to get the CASA approvals and things like that, but the drones are actually owned by SRA.
Thank you. I think someone's just typed a question in the other chat, so I'll just go and grab that. And I'm sorry for the confusion about that. William, I think that was yours, so I'll just copy it and put it into this chat.
Yep.
So this, I hope everybody can see that now. So what is the cost for harvesting a yield trial for TCH compared to estimation? Hang on, sorry. I've got too many things popping up now. Compared to estimation of TCH through HTP. Well, can you see that anyway, Sijesh? Sorry.
Yeah, I can see that
Good.
question. I mean, they're quite cheap. It's a short answer, but I mean, it depends on a lot of factors. But if I have to give a ballpark value for harvesting a cat trial with 3,000 genotypes, I would say the harvesting would cost about $10 per entry. Whereas the drones would cost about $1.05 or $2 per entry. So that would be the ballpark value. So it's quite cheap compared to mission-based harvesting.
And the question from Ben, are you happy to address that, Sijesh?
Yeah, thanks, Ben. Thanks for the question. And I think there's potentially huge opportunities here. As we know that the genomic predictions are quite variable across the different sugarcane growing regions, and one of the things could be the G by E effects. So the phenomics approaches can, if you can include some of those phenotypes in your selection model, they might be able to, improve your selection accuracies. So I think there are potential opportunities here, and hopefully we can, Jason and Sherman can work with you on how we can bring about some of those technologies together.
Would anyone like to ask a question? I don't see any hands raised, but I don't want to miss anything.
Yeah, I can see more questions here from Thiago. Thanks for the Thiago question, Thiago. And so it depends on what we want to get. So the question is, how often do we get data from each stage? So in each stage, we are interested in capturing specific traits. For example, if you want to capture plot gaps in a cat trial, so we would go out and capture those at 3-month stage. And for a fat trial, again, you would mostly capture those data until we have significant competition effects. And once we have significant competition effects, that's where we stop our phenotyping. But as you saw that all the phenotypes that were measured well before competition effects, they are good predictors. So you don't need to wait until they are 12 months age. We can phenotype the crop well before the competition effects, and yeah, we can have. But to answer your question, yeah, it's quite difficult to say exactly how often. It depends on the crop and the traits we want to measure from each trial. Yeah, Raul asked, can we reduce the time for selection? And yes, of course. One way is, but we're not there yet. But I think one way to reduce the cycle time would be if we can, do some sugar prediction as well. If we can do that, then we can have a drone-based yield prediction, drone-based sugar prediction, and thereby, we can entirely skip a return crop and we can go straight to props. So yeah, there is potential to reduce the cycle time, but not just yet. Just need to do a little bit more research into that. Can it be used to evaluate the performance of harvesting? Yeah, I mean, David, there are plenty of opportunities. As we saw, there is so we can generate row lines for harvesting, and also we can generate what is the ratoon loss due to harvesting. So we can have the plot length or plot gaps measured over successive ratoons, and we can say how did the harvester affect the ratooning of the crops. So that would be easily captured using the drone. So if you are talking about ratooning performance and harvest performance, yeah, it's quite easy to capture from the drones. Anthony, for yield prediction, so we use the multispectral camera at the moment. So it's based on NDVI, canopy height, canopy cover, and we are working on including canopy temperature into the equation. So yeah, right now we are using RGB and multispectral cameras for yield estimations. No, we don't, William, we don't do not yet to do the inflorescence, but it's quite possible. We just need to capture the images at the right time. The image processing methods are there. We just need to make sure we capture at the right time to do that, to characterize the clones for inflorescence. Tiago, at this time, the breeders in Burdekin are using the data for selection in the cat and also in the pat stages. So we used the drone data to make some selections in the pat and cat stage. And what we're going to do is, and we're going to evaluate how effective those selections were in successive breeding cycles. And we are in the process of doing that. But this project was supposed to be a validation phase. So this project is going to end in June next year. So once we are past this validation stage, and hopefully we get good results, and then effectively we can go and implement the technology across different breeding programs or different regions. And that's the aim at this point in time. Vigor. Yeah, so for vigor, again, we can use RGB. We can do a spectral classification to get canopy coverage of the plots, and we have seen that canopy coverage is actually quite well correlated with early stage biomass. So yes, we can use the RGB cameras to look at the crop vigor. And we have done that, and we have seen some good correlations with early stage biomass estimations. I don't have any more questions here, Alison.
No, good timing. Oh, okay, maybe one more.
Yeah, of course, David. Yeah, my answer was in relation to harvesting losses. Yes, we can screen the crop over successive ratoons, and we can compare it with the harvester speeds, and we can say how was the harvesting losses. But to provide a real-time feedback, that would be a slightly different ball game, and it's not something that we have the capabilities for at this moment, but it's something we can work on, I guess. But just to have a prediction of harvest losses and how the harvester performance, that's quite possible using the drones.
And there's one more from Juan by the look of it.
Yeah. Yuan, at this stage, we are not actually measuring the erectness of the canopy, but you're right, that could be an important trait. We can try and capture those using the images from the drone if you think that's important. But at this time, we haven't really looked at erectness of the canopy. Yep, I think, David, yep, I think to predict harvesting losses, it's quite easy and quite possible, because we can just have measure the loss in stools, or we can look at how many stools are there in a particular row, and we can look at the loss in stools in successive crops, and hopefully that's what you want to predict the harvester performance and harvesting losses. Yeah. Usually we get for a CAD trial, we usually get multiple measurements per season. It could be anywhere between 6 to 10 flights per season, because we are actually limited by the conditions, the appropriate conditions for flight. So we need a good clear sky and windless conditions to get good phenotypic data. So we are limited by that, but we usually do about 10 flights per season, and we look at the correlations between each flight and G by E between each flight. That's one of the reasons we get good heritabilities with the indirect phenotypes, because we can we can measure the phenotype at different environmental stages, and we can have a good corrections for G by E and have a good phenotype. William, that was on the plans to do some rust phenotyping of sugarcane parents in Moringa, but it was put on hold due to the pandemic. But that's something we are looking at this stage. What we have done is so far is we have looked at red rot, not using the drones, but just using some high throughput imaging in the lab. We were able to predict the rust prevalence in in a high throughput way, instead of waiting for months. I think in a few days. I think Shamshul may have more information about that, but not rust at this stage, but we have just looked at red rot and rust, and other diseases are in the pipeline. I think once we are all vaccinated, I think we're going to fly up to Mering and do some more flights.
All right, given the time, I think we'll call it there, but it's great that there's obviously so much interest in this, and thank you very much, Sijesh, for presenting, and for everyone for attending, and for all of the questions. I might talk to him or talk to Sijesh later and see if there's, do we need to do a follow-up? Is there some way that we need to provide more opportunities for people, because there's obviously so much interest. So whatever the outcome of that discussion is, obviously we'll promote that via the website and send out any notifications via email. So if you don't currently subscribe to our our e-newsletter, that would be the best option for you to sign up to. So you can do that via our website or by contacting me. And we don't have any dates of any upcoming webinars, but there are some sort of plannings in the pipeline for those. So those will also be on our website and sent out via email. Thanks again. If you can take a moment to fill in the form, it's disappearing up the scroll of the chat. I tried to put it in the bottom again, but everybody's so enthusiastic that it's disappeared. But I'm just going to put it in again, just in case that helps get some responses on that, because we really do value your feedback. So thanks again for attending, and we look forward to having you attend future webinars. Have a great day, everybody.
Alison.
Suggest you might get a lot of emails.
Yeah, I guess I didn't answer some of the questions as well as I would like to, or they would like. So yeah, happy to take any more if there is, Alison. Yep. Thanks again for organizing. Yep. Thank you so much.
No problem. All right.
right.
See you later, everyone. Bye-bye.
Bye-bye.